Hi everybody, welcome back to the Feynman technique. Today I'm going to be proving this identity that cosecant squared x is equal to the sum over all the integers n of 1 over x plus pi n squared. All right, so the first thing we're going to need to do is recognize that sine x has roots at n pi, and so therefore has the following form. Um, if it has roots at n pi, let's take the n is equal to 0 example. We need it to have a root at 0, so let's start our function to just be x. But then we need roots at pi and negative pi, so we need another term in our product that's going to have roots at pi and negative pi. So let's start it with 1 minus something. Well, we need it to be equal to 0 at pi, so let's put something over pi. And then if we put x, maybe x squared over pi squared, you'll see that at x is equal to 0, we have a root. At x is equal to pi, we get 1 minus pi squared over pi squared, which is 0. And at negative pi, we get 1 minus negative pi squared, which is pi squared, divided by pi squared, which is 1. 1 minus 1 is 0, so we have a root there. But we also need roots at negative 2 pi and 2 pi. So we can get those roots by just adding a new term and putting a 4 right there. So now you can see we have roots at 2 pi and pi. And then we add another term, and we get this, and then another term for our roots at 4, we can get this, and then it continues. So if we follow this pattern out, we can see that sine x is equal to our first term here, x, and now we represent the rest as an infinite product, that product being the product of all of these a sub n terms. So anyway, yeah, now we have sine of x is equal to this. Well, if that's true, then we can take the natural log on both sides and it will still be true. So we'll do that. We'll take the natural log on both sides. Well, we can split the right-hand side up using the properties of logarithms. And in fact, we can split this up even further, like this. We can use the properties of logarithms to change this into this. And let's think about why. The natural log of a product is just the sum of those natural logs. And we have the natural log of a product. So now we're just summing all of those natural logs together. Okay, so that's how you get from here to here. It's just the properties of logarithms. And next, well, we can take a derivative on both sides. If these are equal, then their derivatives are also equal. So that's the next step. And then we evaluate the derivatives. So on the left-hand side, of course, the derivative of natural log sine x is cotangent x. And then the derivative of natural log x is 1 over x. And then all we need to do is take the derivative term by term of this a sub n. And what you get is this. This is not the final form, but of course you get 1 over the natural log times the derivative of the thing inside the natural log. And you'll notice I omitted the 1 since we don't need to take the derivative of that part since it's 0. And the next step, we just actually evaluate this derivative. And yeah. Next, we're going to simplify this. This can be broken up using partial fraction decomposition like this. If you use partial fraction decomposition, you will see that that is in fact equal to this. So now we have cotangent x. Give me 1 second here. Is that doing that? Okay, there we go. Got rid of that. All right. So now we have cotangent x is just equal to this. All right. Well, we're looking for cosecant squared x, so it makes sense to take a derivative on both sides again. Because if we take a derivative of cotangent x, we get negative There is one more. There is a step that I forgot. Okay, we want to get rid of this 1 over x term because it just doesn't belong there. So what we can do is add the n is equal to 0 term, which happens to be x, by just starting our index at n is equal to 0. And then subtracting the n is equal to 0 term, which I said it was x, but it's actually 1 over x. So we subtract that off, and it gets rid of this 1 over x. So these two expressions are equivalent. Next, you'll notice in this sum, we can just bring all our n's to negative n. The sum over the positive integers of this is just the sum of the negative integers over this. And then you'll notice we have all the integers accounted for, and we have the exact same a sub n, so we can just say that cotangent x is simply equal to the sum over all the integers of 1 over x plus n pi. Next, we can take a derivative on both sides. And the derivative of cotangent x is, of course, negative cosecant squared x, and the derivative term by term of this will just give you this, and then we are done. All we do is multiply both sides by -1, and we arrive at our desired identity. So we actually got two nice identities in this video. We got the cosecant squared x identity, and we also got a cotangent identity. Cotangent x we found was equal to this. So we got two nice identities. We got cotangent x is equal to the sum over the integers of 1 over x plus n pi, and that cosecant squared x is equal to the sum over the integers of 1 over x plus n pi all squared. Anyway, guys, hope you enjoyed that, and we'll see you next time.